U of t convoluted
Y of t equals U of t convolved with what?
e raised to the alpha t
Minus or plus?
minus, sorry, yeah,
Alpha t.
times u of t
Uh-huh.
for alpha is greater than 0.
All right, it's positive. All right, for this one, you draw the two functions. I always recommend you do it. U of t looks like this. If this is t, this is u of t, right? That's the first function. The second function looks like this. It's e to the minus alpha t u of t. That's simply an exponential decay. It's 0, goes like this. Do you all agree with that? Now of those two, which one do you want to leave alone, not flip and shift? The exponential, absolutely. So we'll call this x of tau, right? And replace t with tau. Agreed? Now this becomes, this u of t will be my h of t then. It's the one I'm going to flip and shift. Do you all agree with me? This is a very straightforward problem. It's not a difficult problem once you understand the fundamentals of convolution. So we take this and we flip it first, and that makes it do this. And this is going to be u of minus tau. The axis here now becomes tau, and this is tau. Do you agree with me? You asked the question, do you all see this? Now the point, I call this a curve. It's being drawn this way. This is for t equals 0, the snapshot. Do you agree with me? As t gets bigger, more positive, greater than 0, the point here that it ends is at t. And the argument becomes t minus tau. Do you all follow me? Now go ahead and put in a value for t. Let it be 1, right? If you have 1 minus tau, it's on all the way to 1, and then it's 0 with t equals 1. Do you all agree with me? All right, now the area of overlap, and I use that word overlap, is right here, correct? Convolution says that to get the convolution of those two, y of t is equal to the integral from minus infinity to infinity of x of tau times h of t minus tau d tau. That means you take the product of the two functions, literally a point-by-point multiplication, right? Then you integrate that product, correct? And when you do that, what are you going to get? Well, for this, there's regimes, right? For the convolution y of t would be 0 for t less than 0. Do we agree with that? Everybody. It's as straightforward as it gets. It's as simple as it gets. But for t greater than 0, now I have to integrate from 0 to t e to the minus alpha t, or alpha tau, pardon, d tau. Do you all agree with that? You asked this question, I'm going to ask you. Do you see this? It's very, very straightforward. This is not a difficult one. There's not a lot of tricky things where you don't turn on at 0 and stuff like this, and you don't have 5 domains where you have to worry about what the convolution is for each one. This is a very simple problem. All right, relative to what some of them are. Let me put it to you that way. All right. Now here, what's this going to be? Well, when I integrate that, I get minus 1 over alpha, right? Times e to the minus alpha tau, where tau is evaluated from 0 to t. Just making sure you see the steps. With me?
Yes.
Now, what I do at this point, and I encourage you to do that, when you see a minus sign in front of an evaluation, right there, switch these limits and make it a positive. Got me on that? All right, so just switch the limits, make that 0, make that t. The reason I do this, it'll simplify. You'll get a minus all the time, and sometimes you forget the minus was there, one of the minuses. So do it this way, and then you don't have that problem. And this is simply equal to 1 over alpha, and then we evaluate e to the minus alpha times 0, which is e to the 0, which is 1, minus e to the minus alpha t. And I'm going to just go ahead and put a u of t there for clarity that's only valid for t greater than 0, but I can also simply put the regime t greater than or equal to 0 there. Got me? Now, what you'd be asked to do is a sketch. You asked this, I want to make sure I'm answering every part of your question. So far, so good? When you sketch this, well, if I sketch the convolution, call this y of t versus t, well, it's 0 until you hit 0, right? But at 0, what's the value? Put in t equals 0. It's 1 minus 1 is 0, right? But what is it going to do? It's going to asymptotically approach the value of 1 over alpha, right? Because this term, as t gets big, goes to 0, and I'm left with 1 over alpha, so it's going to look like this. And this would be 1 over alpha. Agreed? It is very straightforward. Do you see that? Did you have any other question about this problem?
No, I for whatever reason, decided to flip and shift the E.
Well, you can do that, but you're making more work for yourself.
I
All right? I'm just telling you, don't make it harder than it already is. Take the simplest function and flip and shift it. It'll be less irritating, I think. All right? I can't promise that. Next question. Let me get rid of this. Anybody?
There was one, it was x of t is equal to g of t convoluted h of t, and I wanted you to prove that x prime of t is the same as g prime of.
What you're talking about is the derivative, right?
Yeah.
I'm not really worried about that one, but I'll show you. Somebody actually sent me an email about that. Is that you, Ruth? Or am I wrong? About somebody, or was it you? You
That was
did.
me, yeah.
All right. So here's what it is. You, what number is that, just for everybody?
Yeah,
4.8.
All right, they say if you have y of t here is equal to g of t convolved with, I'll call it x of t. It doesn't matter. These functions, it's irrelevant what you term these things, right? But the operation is convolution. They want you to prove that dy of t dt, and this would be something you get in a math course. I wouldn't ask this question. Your engineers, your applications oriented. Now, Jitendra Tugnay, Dr. Tugnay might, and a few others, because they are very much into proofs because of they work with information theory and higher level theory, so proofs become a matter of necessity in their work. But in my work, I'm application. Strictly, I use things to, I use all the science and mathematics to actually create things. I don't prove things. I assume they're proved. Just me. All right, they want you to prove that this is equal to dg of t dt convolved with x of t. Now, this is the big deal with these things. The minute you see a proof, you go to the fundamental definition. If you take the fundamental definition of that, it's equal to an integral from minus infinity to infinity of the first function, g of tau, times the second function, h of t minus tau, d tau, right? Actually, I should probably flip this one, sorry. T minus tau, h of tau. Oh, my bad on this one. All right, because I need the t operator in g because of the form of the derivative right there. Got me on this? Now, when you take a derivative of this with respect to time, what happens? Well, these limits don't change, do they, class? This is the only thing that is a function of time, right there. G of t minus tau, understand? So now when I take the derivative of g of t minus tau, d tau, times h of tau, d tau, that is literally defined as the convolution of g, or really a convolution of h of t times convolved with the derivative with respect to t of g of t, if you look at that. It's the definition. You've proved it that way. Do you follow me? Because this operation here comes from this right here, right? And the derivative of that is expressed right there. Can everybody see this, class? That's a simple proof. I'm not going to ask you a proof, but you should at least understand why it's true. Now, here's the problem with this. When I say I want dy dt, and this is the definition of y of t, what people will do is the chain rule. They take the derivative of this times this plus this times the derivative of that, and that would be completely wrong. Understand? And the reason is because the definition of convolution says you only use the derivative operator on one before the convolution, then do the convolution. Understand? Or you could do the convolution, then do the derivative if you want to. In either case, that's the result. Who asked that? All right, good. Next question. I figure I always get plastered with questions right here. Right before the quiz, I usually, what happens at this? Nothing? Oh, yes.
Okay, well, like, say a function is described in terms of, like, let's say u of t. So, u of t minus u of t minus 1. So.
Okay, so you've been looking at all quizzes and tests, and I admire that.
Okay,
So let's just do this one. Let's say that one function, x of t, is equal to u of t minus u of t minus 1. That's simply a pulse. It's on at 0, right? Goes off at 1. We could put a pulse function to describe that too. All right, we can use this if you want, but the pulse function would work just as well. Now go ahead. What do you want to convolve it with?
that was my question.
What does it look like?
Can we just replace it with a pulse
Yeah,
function?
yeah. What would it be? It would be a pulse function of width 1, right?
Yeah.
Centered where?
T is 1.
Minus a half, right? Width is 1. It's centered at a half. Everybody got that? Yeah, I like pulse functions for that reason. They're easy. You only convolve one function. You don't have anything? Nothing? I am shocked. Yes.
I have one. It's from an older homework. If
That's all right.
Okay. It was from 2.14. You're involving like it's a sine, it's piecewise.
Why don't you give me the function? Is this a sine wave, just a positive? All right, let's do it this way. I think what she's saying is this. If we have a function where we have sine of pi t times, and let's call it a pulse of width 1, that's a half, that's 1, and it's t minus 1/2. That's basically the function. I've mathematically expressed it. We'll call that x, right? X of t. What are we convolving it with?
No, it's the sine convolved with the pulse.
That was only one. Isn't it just the one half of a sine wave convolved with something?
And U of A.
It's
U of t?
U of t.
All right, that's right. So this is x of t, and the other function I have, I'm going to call it my h of t, is simply, is it u of t? Right? This is pretty straightforward, right? Everybody got me? You asked me this one, I think. Yeah. Got me on this one, everybody? Now again, I'm going to slow down on this one and make sure everybody sees this. First, you agree that that's a sine wave. Sine pi t exists from 0 to 1. It starts at 0, goes to 0 when t is 1, right? That's a u of t function. That's my h of t. Which one do you want to leave alone and not flip? The sine, and that should be extremely obvious. So now I replace the t here with tau. And really, you don't even need this, because you've got a picture. The picture tells it all, right? And this becomes tau as well. Now, the next thing is I flip this guy. So this is my u of minus tau, correct? Now, this is at t equals 0. Is there any overlap? As a matter of fact, the point right here is right there. That point is t. And I always call it a curtain being drawn when I have u of t's. So the curtain is going to draw this way when I put in the argument t minus tau here. The curtain will draw this way. Right? Agreed? And now it's very observable what's going on. You take a look at this. These two functions are non-zero only from here to here, right? Agreed? So the product, thank God, it's a u of t. 1 times sine of pi t, or sine of pi tau, is just sine of pi tau, right? We integrate sine of pi tau from 0 to t, right? Integral of a sine is minus 1 over pi times the cosine of pi tau, right? So when I go ahead, and I can do this fairly straightforward, I can say y of t equals 0 for t less than 0. Y of t then is the integral from 0 to t of sine of pi tau, d tau, and this would be for t greater than 0, less than 1, or equal to, and then y of t will be a constant. Now, just listen to me now. We'll do the integration right here, but this is a straightforward integration. I think everybody can handle that, right? You're going to get minus 1 over pi times cosine of pi tau, evaluated from 0 to t, and I'll leave that alone for now. It's not hard. I'm trying to optimize the usage of time. This part is the part where now the curtain goes all the way through. It's drawn all the way through here, and it's out here, right? Now the area of overlap becomes the multiplied area, the multiplied functions integrated through the area of overlap will be a constant. Does everybody see that? We're going to do that one First, I'm gonna go ahead and do what this is. Y of t here would be equal to minus 1 over pi cosine of pi tau, evaluated from 0 to t. Does everybody agree with that? Again, I know I'm moving a little quick here. I'm looking at that clock. Better look at this clock. One's probably wrong. Anyway, when I take a look right here, it's the minus sign, right? Again, what do? Flip the limits, get rid of the minus sign. So you just flip them. All right, that's 0, that's t, and that makes this simply 1 over pi times cosine of 0, right? Which is 1 minus cosine here of pi times t. That's what it is for this regime. And the last regime, y of t equals, it's the same integration results here, but now the limits are not from 0 to t, but from 0 to 1, correct, class? So now you get 1 over pi times quantity of 1 minus cosine of pi. Y'all follow me? I replace t with 1 here, correct? What is the cosine of pi? Minus 1, isn't it? Cosine of 0 is 1, cosine of pi is minus 1. Well, 1 minus a minus 1 is 1 plus 1, or 2. It's 2 over pi. And that's what it stays at. Everybody see that, class? Yeah. Did you have a question?
Couldn't you just write it as like t less than 0 and then t greater than 0?
No, because for t, now just listen to me. This is true for t between 0 and 1. If you use this for all t, right? What happens when this is 2? Then this is 1, isn't it? When t is 2, cosine of 2 pi is 1, isn't it? It's the same as cosine of 0. Then you would have 1 minus 1 is 0. Then it would be time varying. But after the curtain's drawn through here, after the curtain's drawn through there, the overlap area is only from 0 to 1 that you integrate through. Can you see that? Never change because it's 0 out here. All this is times 0. All right? So what it would look like if you graphed it was this. This is 1. It's at 0, right? And basically it does this. And it goes to 1 over, or 2 over pi, right here. That's basically a graph of that, okay? A sketch. Another question? All right. Then what I'm going to do is now do discrete time convolution. I'm just going to show you this. This will make a little more sense, I think. You've had continuous time. Discrete time is the same deal. And this one I slow way down for. I assume by now you look through every possible bit of information about what I quizzed you on in the past, and the problems, and God knows what else. The more problems you work, the more you understand in general. And all of a sudden you realize at some point that, oh, I can do any of these. Because frankly, I see what's going on. And even though some may not like to teach convolution from a graphical perspective, it is the most obvious way. Engineers, they like to have an abstract thought process based on visualization as much as possible. All right, so now we're going to do, this is discrete time convolution. This is real important, but I'm going to go through it slow. For discrete time, we have two basic functions. We have all the list of functions we had before, but now instead of t, you have n. Got me on that? Now, n is an integer. -1, 0, +1, +2. It doesn't have a value of a half or pi or anything like that. All integer values for n. So now, when we have this, we're going to say that we have a system where we're going to put in a function, x of n, and we're going to get out a function, y of n. And the system is uniquely identified by the impulse response, h of n. I've done this before, just as before, right? Before it was t, now it's n. The function we have to understand, the two functions are delta of n is simply equal to 1 for n equals 0, and it's equal to 0 else. And u of n equals 1 for n greater than or equal to 0, and it's 0 else. So it's literally like sampling the u function at t equal n. This one's a little different because the magnitude is 1. It is not infinity. That's the only thing. Got me on this? Straightforward, simple to see. Now here's where you have to be careful. Let's go back to the way we started with convolution. We have a system defined as h of n, the impulse response. So when I put in delta of n, I get out h of n. And this is for linear time invariant systems. It's not for nonlinear systems, and it's not systems that vary with time. Got me? Now, when I go ahead and put in delta of n minus I get h of n minus I. Makes sense. That's time invariant. You shift over the input by something, 1, 2, 3, 4. You shift over the output that same amount. Does that make sense to everybody? It should be obvious. You got me on this? Now we take that same expression and we multiply. Remember, this is a function of n, not I. We multiply it by x of I. And if we multiply by x of I, we multiply the output by x of I as well, correct? Isn't that right? You all see what's going on? What do you think my next step is? Take a shot in the dark. Before, what did we do in the next step if it was continuous time? Does anybody remember? No?
You added.
Say?
Added.
Integrated, well, we had this one, sum it, but before, remember then we integrate this side and integrate that side, and we get y of t. Do you all remember that? Mm-hmm. That's the definition of convolution. Here, he said it. Now we do a sum. We say if we sum x of I times delta of n minus I, I'm going to show you what happens here. And this would be from I equals technically minus infinity to infinity. Just look what happens here. Now just think about this. When does this function turn on to a value of 1? When the argument inside there is 0, right? All other values are 0, correct? Mm-hmm. So the only value of x it's going to pick out is the value when I equals n. Do you all see that? So that means this is x of n, and voila, that is my input, x of n. For any value of x of n, right? Now out here, what I do to get my output, my y of n, I simply sum these from n equals minus infinity to infinity of x of, n, not n, I equals minus infinity to infinity of x of I times h of n minus I. And voila. And instead of integration, we have summation, because it's discrete time. Okay? Now this is straightforward. You can almost visualize this if you actually plot a few things. If, well, I'll tell you what, today we're not going to have enough time to plot a bunch of these, but you all see what's going on here, class? So let's, just for the sake of visualization, I'm going to give you a problem and we're going to work it in the discrete time domain. And I'll show you some tricks on this too. I don't think I'll have enough time today. But let's go ahead and do this one. And by the way, the rules of the game before still apply here. If you're given two functions, the one with the most going on, you leave alone, and it will be a function of I. See, that's x of I? The one with the most, you're going to flip and shift. Everybody got that? As a matter of fact, it's going to make perfect sense to you, I think, if you've been paying attention. So here's two functions. I'm going to call this function x of n, and I'm going to have it just like this. It's going to have three values, all 1. Okay? Boy, that looks like a pulse to me. As a matter of fact, it is a pulse, but just look at the values for now. My second function over here, which I'll call h of n, is going to look like this. It's just going to be, I'm going to make it equal to u of n. So it's just a row of, call it a bed of nails, right? Just all the way down there. It goes on forever. That's n here, and this is n here. But these only have 3 values, and all the other values are 0. Right? This would be 1, 2, 3. Now, which one has the most going on? You might go for that one. But actually, this only has 2 regions where it's defined differently. For n less than 0, this would be 0. Right? This would be minus 1. For n less than 0, it's 0. For n greater than 0, it's 1. You all see that? This is the one we're going to flip and shift. We're going to leave this one alone. You understand my reasoning? Because here it's 0 from minus infinity to minus 1. Then it takes on the value of 1 from 0 to 2. Then it goes to 0 again. So there's 3 regimes. That's the one you leave alone. So now we take this, and instead of making it n, we make it I. This is I. And this is in keeping with this form here. You all see that? The sum is on I. All right? Now you go ahead and you flip around the axis, that one, and start shifting. When we flip this one, my u of minus n, right? It's basically 1 all the way. It's got a value 1, 1, 1. And at 0, it's 1 as well, right? And then it's 0 on up here. Now you can see if n was minus 1, it would start here. Do you all see that? Sorry, that's minus I. I'm bad about this. That's I, correct? That's when there's no shift, but there is already an overlap, isn't there, class? This first one times this one is already giving a product that's not 0. Do you see me on this one? Now, what I'm going to do is say, if it was 0, if this argument was the argument there, which is n minus I, then this would be, if say n was equal to minus 1, then this would be the function. It goes down to 0 like that. You see what I'm saying? There's no overlap there. We're going to go ahead and say this is like the curtain, and this value right here is the value n. And it's just like the value t before. Remember, we had tau on this axis, and then we had t, and the curtain was being drawn with t, right? Now n defines the point where it stops, right? Now when you look at this, just take a look at that. You can do this. When I look at this, if I want to know what the convolution of this is, y of n, it's 0 for n less than or equal to minus 1. Everybody see that? Evident? It's clear, isn't it? Now, for n greater than or equal to 0, and now we have to think about this. At 0, this first spike is there, right? At 1, it's here. At 2, it's here, right, class? Now, if I go past that, all of a sudden I'm not picking up any more overlapped area, if you think about it that way. You can actually sketch a little window here. Sketch a window here and think, well, if these are continuous time things, right to this point is where I want to stop. So now I'm going to say equal to 2. And what is the value y of n? I bet you're going to see this in a heartbeat. Well, when n is 0, it's 1, right? When n is 1, it would be 1 times 1, 1 times 1. Add them together, it would be 2. Follow me? When n is 2, I got 1, 2, 3 spikes, right? It would be 3, correct? So you would write this as what? Now think about this. The value here would be what? 1 plus n, wouldn't it? You can play with this later, and I'll show you some tricks. You all see this? Because it's a summation that starts here and ends at n of the product of these two. All right? It's just think of continuous time and what you would have done in continuous time. Same here, only now it's just at discrete points. But what happens when n greater than 2? I want you to just think about this. Well, look, just put as many spikes as you want here, right? N greater than 2. The area that overlaps is this area right here between 0 and 2, right? And how many values? I have 1 times 1 equal 1, 1 times 1, 1, 1 times 1. So you have 1 plus 1 plus 1, 3, right? And from then on, it's 3. Got me? And that's all she wrote, gentlemen, ladies and gentlemen. Now, I know I may be oversimplifying this, but I want you to realize the similarities from what I just showed you here and what you've learned with continuous time. Now it's just picking points, right? And it's still the same deal, right? And instead of an integration, it's a simple summation. But I'll show you a lot of tricks to this, all right? I can't today on how to manipulate these things. And this is a valuable thing. Everything, just about everything we do with most signal processing, it's digital signal processing, it's in the discrete domain, all right? It's always at discrete points. And so everything's indexed with with integer values, and all the processing is done that way. One other thing I'll tell you, you're young enough, you love music, right? You remember you had soundboards and you had these equalizers, you ever see these things, like Winamp or whatever you call them, and you can move the things around. Well, that's a digital signal processing way of modifying the sound quality. And what it's based on is an actual real, call it an audio event, is actually first measured with something and a voltage is developed proportional to that with a transducer. That's a microphone. Then when you have that, that signal is then sampled at a very high rate of speed. Then everything that's sampled is going to have to be in a quantized levels. There are only maybe 1024 or maybe 512 levels. So the closest voltage level that is associated with one of these integers, it'll go to. Now that introduces quantization error. The rate that you sample, you're going to see, is defined by a Nyquist criteria that we'll talk about later. And secondly, the quantization error becomes critical for fidelity. All right, so when you take that, do signal processing, then reproduce the sound, it won't be distorted. You had a question? Did you have a question?
No, I was stretching.
All right. All right. And now I wanted to give you enough time for your quiz. I usually give you about this much time. Actually, let me just leave that out there. I'll hand it out. Could you take everything off your desk, any wearable electronics, take your phones out and put it flat on your desk upside down?